last talk of this workshop will be on tropical circuits, and Tuukka will tell us.
Thanks for the introduction, and thanks for the organizers for inviting me to give a talk here. And thanks all for joining the very last talk of the last session. Yeah, so I don't usually do any algebraic stuff or any complexity stuff either. About 5 years ago, I wrote one paper about tropical circuits. So that's how I ended up here, I guess. Okay, so let's start with what are tropical circuits. So they are circuits where the operations are plus and max. So here we have inputs bottom and output on the top. And you can see what they compute. They compute these tropical polynomials. So here you have summation over all monomials turns to max over monomials, and the monomials turn out to be these linear combinations of variables, but maybe an important thing, they're not really like general linear combinations, but it's like the exponent comes to the forward, so that it's like this coefficient here is really the exponent, so it's always a positive integer actually. And then like the coefficient, it comes as like plus constant. So this is how I think of polynomials now. Yeah. Okay, yeah, so this tropical circuits are the circuits over the max plus semiring or the min plus semiring. And they were first studied already in the 80s by in the paper of Jerome and Schneer. And recently, Stasis Jukna wrote many papers about tropical circuits. I wrote one paper, and Kluka Nederklof wrote one paper also recently. Okay. So why I care about tropical circuits and why people have argued to care about them is that they model somehow a pure dynamic programming algorithms for optimization problems. So you can think of an optimization problem. You take a maximum over all solutions, and now each solution is maybe a sum over some variables given in the input. So you can think, for example, we have like the shortest SD path. So what we're taking like a, okay, in this case minimum, we're taking minimum over all paths in a graph. Okay, so what we have the inputs are like edge weights of a graph, and we can assume, let's say it's a complete n-vertex graph with two vertices and t, and we are taking minimum over all SD paths, and for each of these paths we are summing over the edges on the path. Then you can have well, the permanent maximum perfect bipartite matching. So here we have we're taking maximum, and now we're ranging over all perfect matchings in a complete bipartite graph, and the inputs are the edge weights, and we want to find and what this is doing is finding the maximum weight of a perfect matching. And yeah, both of these are polynomial time solvable, but only shortest SD path has polynomial size tropical circuits. So you can think of like this, where we cannot solve the maximum perfect matching via a pure dynamic programming algorithm, while we can solve shortest SD path via a dynamic programming algorithm, a pure dynamic programming algorithm in some sense. And my definition of, okay, what is pure dynamic programming algorithm? It's a tropical circuit. So this is kind of a circular definition up here. So for shortest SD path, we can have these polynomial size circuits from Bellman-Ford algorithm, and we have for like this maximum perfect bipartite matching. Already Jerome and Schneer proved that you need exponential tropical circuits. But actually, yeah, there's one important definition I have not given. So can the inputs be negative? So actually, if we want to say that the circuit needs to work properly for all, let's say, inputs, for inputs that can be both like negative and positive numbers, then actually for this definition of shortest SD path, we don't have a good tropical circuit, because it's like the maximum length path. So it's like Hamiltonian SD path. So here, this one only works when you have an assumption that the inputs are non-negative numbers. Let's say I don't really care what number, maybe integers, maybe reals. This doesn't really matter, but like negativity matters a lot. But it can also be kind of yeah. So shortest SD path becomes hard, and this was proven by Jerman's this paper where they proved a lot of things. But okay, I guess for shortest SD path, you can fix this by changing the definition so that maybe P, instead of ranging over all paths, it ranges over like all walks of length up to n edges. Yeah.
When you say input, do you mean the values that the variables will take, or do you mean the coefficients that you
the values that the variables will take?
Can I use negative coefficients in the circuit?
So negative constants. Let's say typically you're not using basically any constant, because they always end up in the output, and then if the output should output like 0 when you give all zeros, then it's a bit strange if there is some coefficients. So typically there are none of these input constants, I would say. But yeah, I guess in this definition they can be negative. Yeah.
When you define tropical circuits, you said you could either use a max or a min outside. In the previous slide, maybe.
Yeah.
Was it like a max? Was it supposed to be max or min?
So you can use max. So these are different settings: max plus semiring or the min plus semiring. But you cannot use both.
Right.
Yeah.
And if you go to the next.
And now, if you allow negative, then it's like if you allow like both negative and positive inputs, then like max plus and min plus turn out to be like the same, right? Because you can negate the inputs and the coefficients, I guess. Yeah. Does it make sense?
Yes.
Good. Okay. And yeah. Typically, like one case that I care in this talk is like if you have if you're optimizing over like a downwards closed solution sets. So you have like you're taking yeah, like if you have some if something is a solution, then all subsets are also solutions. Then like you can turn like something that works for only non-negative weights to something that works out for negative weights also by just putting this gadget with the inputs. Yeah, but for okay, for rest of the talk, let's assume the inputs can be negative, so they are like arbitrary reals. But this is not. This is a bit maybe non-standard assumption. At least like Yukna in his book about tropical circuits, he says that these ones, this is the less interesting case. Like the more interesting case is the one where they're required to be non-negative. So maybe take this assumption with a grain of salt. So this define a bit of different kinds of things. Yeah. Okay. Anyway, let's go forward. So. Okay, so one problem where I looked into this tropical circuits is maximum weight independent sets. So you have a graph and you have weights on the vertices, and you have to output the maximum weight of an independent set in the graph. And what was my kind of observation, that a lot of algorithms for maximum weight independent set, both theoretical and practical algorithms, they implicitly produce tropical circuits for maximum weight independent set. And here is like, for every graph you have a different tropical circuit. So it's like how the algorithm works. It's like it gets this graph and weights as an input. And actually the algorithm, it only looks at the structure of the graph, not on the weights. And it kind of implicitly computes a tropical circuit, and then it only later like looks at the weights only via this tropical circuit. And this is actually like kind of maybe personal story, like I was actually implementing algorithms for maximum weight independent set. Like I tried to look how some graph theoretical techniques would work in practice. And I noticed that everything that I'm doing kind of just uses this plus and max operations on the input weights. And then I looked, noticed, okay, these give these circuits, and I Googled if somebody had looked into these circuits, and I found this work of Yukna, and this is how I got into this business. Yeah, and so like in theory, like all these like things we care in like graph algorithms, like this bounded tree with bounded click with chordal graphs, blah 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 graphs. These algorithms for maximum weight independent set work efficiently. They work via tropical circuits. So you can maybe see, wait, it's all tropical circuits, but this is not true. Actually, there are a lot of non-examples, also a lot of very important algorithms for maximum weight independent set that don't produce tropical circuits. So you have like, say, bipartite graphs, or more generally perfect graphs, where you have to do like, so bipartite graph is like bipartite matching, and for this, yeah, we don't have these efficient tropical circuits, and then you have these like line graphs that really like model the matching problem, and yeah, they're also like you can solve them efficiently by some kind of algorithms that use cancellations, so they are not pure dynamic programming algorithms.
For perfect graphs, though, you don't even have a combinatorial algorithm to begin with, right?
Yeah, I guess so. Yes, that's correct for the yeah, perfect graphs, I guess. Like bipartite graphs you have, yeah. And okay, so that's that. So okay, let me say something about what I proved for maximum weight independent sets. So I guess yeah, you can think of like at least in my research, like my ultimate goal is maybe to understand how the hardness of a problem depends on the input structure. But this is very difficult, even if we assume all kinds of complexity assumptions like exponential time hypothesis and so on. But maybe an easier goal would be to understand how the complexity of pure dynamic programming for maximum weight independent set depends on the graph G. So if we define like tau of G to be the size of the smallest tropical circuit for computing maximum weight independent set on the graph G, can we actually understand how this depends on the G? And what I proved is I proved a couple of theorems. So one of them is like, for every graph that has a tree with k and a maximum degree delta, you have a lower bound on the tropical circuit size that is exponential in k divided by delta, and then the standard dynamic programming gives an upper bound that matches when delta is a constant. And these are like these are tight bounds, but the thing here is of course they're not tight for every graph, but in general, like this is the tightest result you can prove like this. So you need to divide by the max degree if you want to just.
Is there a factor n missing on the left?
Yeah, on the left you cannot have a factor of n. Yeah, so you can have I mean you can have like that the hardness comes from a really small place, and then there's just like n isolated vertices. So you can have maybe plus n on the left. Yeah. So yeah, so it's also not tied up to n. So, but yeah, whatever. I guess it's yeah. Yeah, and then I proved something similar for like planar graphs. Now you have like again tree which explains exactly this this function. Okay, let me say something about the techniques here they use. Like this is the very standard thing in these monotone models. I think we have heard today like at least one or two talks with these techniques. Like you have this a polynomial, and now if you have a like circuit of size s, you can write it as like a sum of products. So it's now max of sums of like of s products. So this is like a very old technique. So this is like the rectangle decomposition. And now you want to say that, okay, you want to write this that like typically you want to say that each of these is like balanced. But now so typically what you do, you have like an expander graph and these are balanced, but what I'm saying is actually you can, all your expander graph proofs probably work also for like, if you take any graph of high tree width and balance this with respect to the tree width, so you can prove your expander graph lower bounds also for all graphs of like tree width k. So you have, okay, so in this case what happens is product, it needs to correspond to a vertex separator, like this, like the variables here in the A should be here, and the variables in B should be here, and this between should be a separator. And the separator should be large because we balance them with the tree width thing. And then like this lower bound with the degree, this is a nice, like, okay, to get the like some bad dependency on the delta, you can do something simpler, but what was fun is that like you get the optimal dependency with the lowest local lemma. And yeah, for planar graphs, I use some induced minor stuff. So this is like something about graph theory. Okay, maybe I'll not say anything more about the proof. And then some open problems about this work, like tropical circuits and maximum weight element sets. So what's still open is to really understand this tau of G for all graphs G, and we have a conjecture that this could be like at least up to quasi-polynomials may be characterized by excluded grid-induced minors. So this is like this is a grid graph, and induced minor is like a minor, but it has to be you cannot do edge divisions kind of. It's like induced subgraph flavor minor, but this is this conjecture is very much open, and in particular, like, okay, what we have like the lower bound side actually, but we don't have the upper bound, so we don't actually know if maximum weight element set is like solvable efficiently on graphs not containing these grid-induced minors. So that's one problem that I looked a lot for past few years, and a lot of people actually in the like graph algorithms community have looked into. Yeah, okay, but this is mostly about graph algorithms, not about tropical circuits. Okay, so let's go forward and a bit more about tropical circuits. So yeah, I was asked to give this as kind of a bit survey talk. So let me also mention another recent result about tropical circuit lower bounds. This is also related to tree width. Okay, so this is about TSP on graphs of bounded tree width. And here again, I guess we first have a graph and then we can design the circuit. And like the simple dynamic programming algorithm for solving TSP on tree width K graphs, it builds a circuit of like this size, like exponential in the tree width is K, so it's exponential in K log K. And then there's more advanced algorithm that uses like the isolation lemma and some like kind of non-monotone parity stuff that gets this down to like this to the of K. And now you can ask so this first one produces a tropical circuit and this one for sure does not. And now Kluk and Nederhoff, they were recently, they managed to prove that, okay, if you want to produce a tropical circuit, then you cannot match this algorithm. So you have this lower bound of exponential in K log K. So it doesn't match this one, but it's at least exclude like this. And this is not for like all graphs type of result, but this is there exists some tree with K graph for which we have this. And this is as maybe interesting method of proving is like this connects to the like some communication complexity stuff, especially like about this matchings compatibility matrix. So it's about like communication complexity where you have like two matchings and you want to figure out if the union of them is Hamiltonian cycle or something like this. Yeah. Yes, and here is an open problem to improve this to match that one. Okay, one more thing I want to talk about is tropical versus monotone arithmetic. So yeah, so tropical and monotone arithmetic are kind of close to each other. So typically, yeah, we have lower bounds for tropical circuits imply lower bounds for like corresponding monotone arithmetic circuits, and most of the upper bounds for tropical circuits also actually they produce like monotone arithmetic circuits. So, but this is just most of this, not all. And this like gives kind of general question like if we can optimize efficiently, optimize using these tropical circuits, can we also count efficiently? And yeah, there are some graph classes, but these are actually a bit esoteric graph classes, but there are graph classes where we know poly-size tropical circuits for maximum weight independent set, but for which counting independent sets in polynomial time is open. But interestingly, I didn't find any such graph class where counting is known to be like sharply hard. So in general, we could ask a question: does there exist a polynomial that is like naturally corresponds to this kind of optimization over sets? So let's say multilinear 0-1 coefficients, and on the like in the arithmetic case, it's hard for monotone arithmetic circuits, and on the tropical case, it's easy. And here we want to work for negative weights because, yeah, we want this assumption here because otherwise you can have some stupid things where you have like just one huge monomial that covers everything, and then kind of what happens below that doesn't matter for tropical, but matters for arithmetic. But this kind of excludes that. Yeah, so this is kind of about the power of idempotence in this monotonic computation. Like you can think, what in this setting, what more power does tropical circuit have compared to monotone arithmetic circuits? Is that it has idempotence, so like x plus x equals x instead of like in the monotone arithmetic you cannot this doesn't hold. And yeah, I think like here. So I haven't proven this, but I think like quasi-polynomial separation should be doable. This is, I believe, like you can think of this upper bound is given by some color coding argument, while like this lower bound is like some W1 hard problem. But yeah, it's not clear how I would go about proving like exponential separation here at all. Like I'm not sure if I even believe in exponential separation here. It would be nice to hear if somebody knows if this is related to any problem. Yeah. Yeah, so I guess that's all I want to talk about. So yeah, so in conclusion, we care about tropical circuits because they model these pure dynamic programming algorithms. And I mentioned a couple of open problems, so characterize which graphs have poly-size tropical circuits for max weight independent sets, and prove this better lower bound for tropical circuits for TSP on trivial K-graphs, and then this one like separation between tropical and monotone arithmetic circuits for this kind of natural optimization problems. And that's all. Thanks.
So you have this, your last slide pretty much. If you have a model that's capturing essentially dynamic programming, have you tried to maybe not compare it to monotone circuits, but maybe monotone algebraic branching programs? Because I mean, those are also pretty directly some model of capturing dynamic programming.
Yeah, so I guess branching programs, they are more restricted, right? Like than circuits. So I would assume they should be quite clear that they're weaker. But yeah, I haven't done this. No. Yeah, but I would conjecture that like in this like independent set thing, like if circuits correspond to tree width, then branching programs correspond to path width. Typically, that's what happens. But I don't know.
Any other questions?
Question 3, the open problem, can you separate if the coefficients are not 0, 1 but something else?
Yeah, like, okay, we can talk about this, but this is kind of, this separation exists if you if you allow complicated coefficients for the arithmetic circuit, but just have like 0, 1 coefficients for the tropical circuit, so like the most natural case is the 0, 1 coefficient. Like, yeah. I'm not sure what happens if you allow in general like strange coefficients for both of them. Yeah.
Okay, if there's no further question, let's thank the speaker.